Welcome to ChemDoodle Shorts. I'm Mary, your ChemDoodle Pro. Let's learn about VSEPR Theory and the Trigonal Bipyramidal geometry. VSEPR Theory, which stands for Valence Shell Electron Pair Repulsion, is a model used to predict the geometry of a molecule based on the electron pairs on a central atom. Those electron pairs in bonds or lone pairs minimize repulsions by maximizing their distance from each other. Let's consider the geometries of molecules with 5 regions of high electron density about the central atom. Let's begin with a molecule with 5 atoms bonded to a central atom. In phosphorus pentafluoride, phosphorus is a central atom with 5 atoms of fluorine attached. To minimize electrostatic repulsions, phosphorus pentafluoride adopts a trigonal bipyramidal molecular geometry. Picture the 3 fluorine atoms around the middle forming a triangle about the central phosphorus atom. These 3 fluorine atoms are in equatorial positions and form the triangle base of a pyramid. Imagine the fluorine atom above the central phosphorus atom as the peak of that pyramid. The fluorine atom below the central phosphorus atom forms the peak of a second pyramid that's upside down, hence the name trigonal bipyramidal. What are the bond angles in a trigonal bipyramidal molecule? To measure an angle in ChemDoodle 3D, select Measure Angle in the Measurements palette. Then select the 3 atoms and/or electrons that make up the angle of interest. Be sure the second selection is the vertex. The 2 axial fluorine atoms, the ones positioned up and down, are in a line with the central phosphorus atom. As expected, the bond angle between these 2 fluorine atoms is 180 degrees. As such, the bond angle between an axial fluorine and an equatorial fluorine is 90 degrees. What about the bond angle between the equatorial atoms? The 3 equatorial fluorine atoms form a flat triangle shape. Its bond angle is 120 degrees, just like the bond angle in the trigonal planar molecular geometry. What if one of the atoms was a lone pair? In sulfur tetrafluoride, sulfur is the central atom. It is surrounded by 4 atoms of fluorine and 1 lone pair, for a total of 5 domains of high electron density. VSEPR theory predicts that sulfur tetrafluoride will arrange in a seesaw molecular geometry. When turned this way, we see why it's called seesaw. Because it looks like a seesaw, the playground equipment that goes up on one end while the other end goes down, and vice versa. With 5 regions of high electron density, sulfur tetrafluoride has a similar shape to the trigonal bipyramidal geometry. There are 2 axial fluorine atoms, one up and one down. In the equatorial positions, there are 2 fluorine atoms in the middle and 1 lone pair. Just as in the trigonal bipyramidal geometry, the bond angle between the 2 axial fluorine atoms is 180 degrees. The bond angle between an axial fluorine and an equatorial fluorine is 90 degrees. And the bond angle between the 2 equatorial fluorine atoms is 120 degrees. Similarly, the angle between an equatorial fluorine and the lone pair is 120 degrees. In the equatorial position, the lone pair has more space, therefore less repulsion, as it is 120 degrees from either equatorial fluorine. If the lone pair was in an axial position, it would have less space, and therefore more repulsion, as it would be only 90 degrees from another atom. So the lone pair prefers to occupy an equatorial position. What if there were 2 lone pairs? In chlorine trifluoride, chlorine is the central atom. There are 3 atoms of fluorine attached and 2 lone pairs, totaling 5 regions of high electron density. This molecule adopts a T-shaped molecular geometry. When oriented in this way, we see that it's aptly named T-shaped because the atoms form the letter T. In this T-shaped molecule, 2 atoms of fluorine are axial, one above and one below the central chlorine atom. The third fluorine atom and 2 lone pairs are equatorial. Recall that in a seesaw shape, the lone pair in the equatorial position has more space than in an axial position, thus minimizing electrostatic repulsion. This idea applies to the 2 lone pairs in the T-shaped chlorine trifluoride. In the equatorial positions, the two lone pairs have more space than in axial positions, and thereby are able to minimize repulsions and maximize their distance from other atoms. Like other trigonal bipyramidal shapes, the bond angle between the two axial fluorine atoms is 180 degrees. The bond angle between an axial fluorine and an equatorial fluorine is 90 degrees. Finally, let's consider a molecule with three lone pairs. Xenon difluoride has a central xenon atom connected to two fluorine atoms and three lone pairs. VSEPR theory predicts that it will arrange into a linear molecular geometry. The two fluorine atoms are in axial positions as far from each other as possible on opposite sides of the central xenon atom. As seen in the seesaw and T-shaped geometries, the three lone pairs are in equatorial positions for more space so as to minimize electrostatic repulsions. The bond angle between the fluorine atoms is 180 degrees. VSEPR theory is a useful model for predicting the arrangement of atoms in a molecule based upon a central atom's valence shell electrons and the repulsion between these regions of high electron density. When there are 5 domains of high electron density, VSEPR theory predicts that molecules can adopt one of the following structures: trigonal bipyramidal, seesaw, T-shaped, and linear. Thanks for watching ChemDoodle Shorts.